Thank you.
Okay. Oh, I know this, but I get to, do I tell a story? No, I won't. It is my pleasure to introduce the next speaker, Dr. Linsey Marr, who is the Charles P. Lunsford Professor of Civil and Environmental Engineering at Virginia Tech. And today she's going to tell us about the effect of humidity on the chemical and biological particles in indoor air. Linsey?
Thank you very much for the introduction, and thank you for inviting me. It's a bit exciting to talk about something besides just viruses. Humidity, of course, is not directly a source of particles in indoor air. It does affect the chemistry and biology of things that are in the air. So this is a bit of a smorgasbord of a talk where I'll cover humidifiers as sources of particulate matter. We'll look at the microbiology of indoor air briefly, bacteria, viruses, and fungi, and how they survive as a function of how humidity affects their survival. And then finally, we'll look at pH and chemistry and kind of some interactions with humidity and how that might affect indoor air quality. Just as a kind of, I think we all know that, oh, if it's hot and humid, we know what that feels like. If it's cold and dry, we know what that feels like. But we often don't think much about these measures of water vapor in the air. So absolute humidity is just a concentration. It can be anywhere from 0 in the very driest types of situations up to 40 grams per cubic meter. And then the relative humidity is the amount of water vapor that's in the air compared to the maximum amount that the air can hold. So I like to think about it as a sponge where maybe there's 5 milliliters of water in this sponge, but the sponge can actually hold 10 milliliters. Well, that gives you a relative humidity of 50%. The size of the sponge depends on the temperature. So at a higher temperature, you have a bigger sponge. Now we have the same amount of water, 5 mils in there, but our sponge can actually hold 15 mils. So now our relative humidity is only 33%. What does this matter for indoor air? I'm not sure that it matters that much. And if you're looking at relationships, because absolute and relative humidity are going to be strongly correlated indoors because the temperature falls within a narrow range. And how do indoor and outdoor humidity relate to each other? Well, there's surprisingly little data out there on indoor humidity. And so studies that have looked at health effects and climate have relied on outdoor data. There's a couple of papers that have looked at the indoor to outdoor relationship in Boston and then in a few places around the world. We have a manuscript that'll be out soon looking at it in tropical regions. So the left figure shows absolute humidity measured indoors. That was in my office in purple, and outdoors in Blacksburg, Virginia, which has 4 seasons, in green over the course of a little more than a year. And you can see that they track each other except for the summer period. And that's when the air conditioning is running. And of course, that condenses, removes water vapor from the air. Now, if you could go over to the right-hand side, you'll see relative humidity. And the indoor relative humidity shown in purple does not match the outdoor relative humidity at all, which is all over the place over the course of the year. But the indoor relative humidity in purple is kind of similar, is correlated with the absolute humidity that's indoors and outdoors again, except for the summertime. And so this is for a temperate region. The pattern differs in tropical regions. Humidifiers can be a source of particulate matter indoors. We're probably told that we should use deionized water or distilled water in our humidifiers, but who really does that? I've filled many humidifiers with tap water, and that tap water is not pure. And so dissolved minerals and other things in the tap water, or even undissolved solids, can be aerosolized if you have some type of nebulizing or ultrasonic humidifier. Dr. Vance might recognize this humidifier. I think it's one that we've used to study nanoparticle emissions too, engineered nanoparticle emissions. And so the figure on the lower left shows the size distribution. The y-axis should actually show it normalized to the particle diameter bins, but deionized water shown at the open circles produces fairly low particles, as you might expect. This is measured 30 centimeters away from the humidifier. And these are not just water particles or droplets, because you can see that the size distribution depends on the composition of the water. So when we have low total dissolved solids and low hardness, we have a kind of a smaller sizes, but they're still pretty high in number. When we had high total dissolved solids, the size shifted over to the right a little bit. You can see it's actually bimodal distribution, somewhere around maybe 100 to 200 nanometers is one mode, and then over larger than 200, there's another mode. The hardness doesn't seem to matter that much, except for a little spot in there, the difference between the green and the red. Now, in terms of mass concentration, the lower right graph shows that with water containing high total dissolved solids and high hardness, you can get concentrations, these are steady state, mass concentrations of over 100 micrograms per cubic meter of particulate matter in your air, where a lot of that is in this very small size range, less than 0.25 microns. This was measured using a cascade impactor. And so really anything where you have high total dissolved solids, you do get quite a bit of mass of particulate matter in the air. So this is one, and these are the chemical composition here. We're talking about minerals, so magnesium, sodium, bicarbonate, calcium, those types of compounds. And now humidity has a large effect on the viability of bacteria and viruses that are in the air. So the top figures here show aerosols. The left panels show bacteria, 3 different types of bacteria. And these are kind of representative of things that we're concerned about as human pathogens. And you can see that the relative viability is lower at low humidity. It's not surprising. Bacteria need their water, and if they don't have it, they're not going to survive. So there's maybe a factor of 10. This is log scale difference, at least for the bacteria shown in red and black, the Mycobacterium, which is a surrogate for the tuberculosis bacteria, and also for Bacillus. E. coli really doesn't do well when it's dry. The bottom figures show the same relationship, but for stationary droplets sitting on plastic. Now, the right set of graphs shows bacteriophages that we use as models for human pathogens. The most relevant one is Phi6, which is an enveloped virus, which has, in all the studies we've done, shows very similar behavior to influenza virus and now to SARS-CoV-2. But you can see that both of our bacteriophages, the Phi6 and the MS2, enveloped and unenveloped, show a decrease in viability of almost 1 to 2 orders of magnitude at these mid-range humidities. And that's true in both aerosols and in the stationary droplets. And so why is this happening? Well, relative humidity is important for chemistry because it controls evaporation and condensation of water, deliquescence. So if we start with something that's from a saturated environment, such as our respiratory tract, a respiratory droplet that contains salts and proteins and maybe a virus, and we expose it to ambient humidity, which is going to be less than saturated, the Kohler equation will tell us, at equilibrium, what the final diameter of that is. So the y-axis here shows the ratio of the final to the initial diameter, where 1 means that there's no evaporation, 0.5 would means that it shrinks in size by half in terms of diameter. And that depends on the molecular weights of the compounds involved and surface tension and other factors. But you can see that if we get down to 20% relative humidity, the final diameter is 0.4, 40% of the initial diameter, or if we started with something that was 10 microns, it would end up as 4 microns. And we lose the water, but of course there's non-volatile components that then become more concentrated. And notice that at 80% relative humidity, we're already kind of shrunken most of the way to that 0.4 number. So really things are interesting between kind of 80 and 100%, but once you get below 80% relative humidity, if you're at equilibrium, things mostly shrink to a similar size. But the dynamics matter, as we've seen in Dr. Farmer's talk and also Dr. Waring's and I think others. Let's say I spill a drop of water on the countertop in the kitchen. Unless the air is totally saturated, we're at 100% humidity, that is going to evaporate completely eventually, right? The equilibrium state is that it's gone. It's all into the vapor phase. But the rate of evaporation really matters, and that's controlled by the relative humidity. And so this figure shows you with some of our droplets, we looked at kind of just weighed them on a balance over time and saw that there's huge differences where at high relative humidity you have a very slow evaporation. So we lose only 20% of the weight over an hour period, whereas at low relative humidity, the evaporation is very quick. Within 20 minutes, our droplets, and these are, I think they started out as 1 microliter in volume, which corresponds to about 1 millimeter diameter, roughly. Now, because of this dynamic change in volume, we see a dynamic change in our solute concentrations, where at very high relative humidity, right, the evaporation is slow, and so there's going to be a small change in concentrations of our solutes. But at low relative humidity, we can have complete evaporation quickly, and then this line goes vertical, where the enrichment factor, kind of the number of times that the solutes become concentrated, basically goes infinite, but it dries out, so then it's no longer relevant if it fully dries out. Now, I think what is interesting is that these medium relative humidities, we see slower evaporation, it's incomplete. I think it's probably forming some kind of gel eventually, where it's kind of semi-solid, but you can see there we get this enrichment factor. Things become concentrated by a factor of 40 and then slowly increase over time over that hour period to almost a enrichment factor of 70. So there's this long period where you can have really, really high solute concentrations and very different chemistry. Lastly, on the microorganisms, I don't study this, but I think mold, which is a subset of fungi, is vastly underappreciated. Of all the calls and emails I'd gotten from the public before the pandemic, at least, I would say 90% of them were related to mold. And so mold is thought to be a problem in anywhere from 18 to 50% of buildings in the US. Mold releases spores. These are allergens, and they are their size is 2 to 100 microns. So right in that range of particulate matter that we're talking about. It is associated with, as shown in the lower left-hand graph, exposure to mold is associated with upper respiratory tract symptoms, cough, wheeze, asthma, all kinds of health problems that, again, I think somehow this is overlooked. There are a couple of people in this area who study this, Jordan Peccia and Mark Mendel and some others, but there hasn't been a lot of activity. And so I tried to do a literature search this morning, actually, for emission rates of spores, right? Because one of the basic things that we like to know about a contaminant of concern is, what is the emission rate? What is the source strength? I couldn't find anything on emission rates of spores. I did find kind of global fluxes of spores, but that's, that applies outdoors. So indoors, where this is causing the problem, I'm not sure we know a lot about this in kind of from the air quality engineering, atmospheric chemistry point of view. And then mold also releases microbial volatile organic compounds, and the chemistry and toxicity of these is also greatly underexplored, I think. And I mentioned that with humidity because mold, of course, is a problem at higher humidity. Now, I'd like to finish up by talking about pH in droplets, because this is something that we found was really interesting and somewhat surprising. So the pH, of course, is really important for reactions. We have acid catalyzed reactions. It controls phase separation in some case, microbe survival, as I'll show you in a bit. And there's an interaction with relative humidity. So a standard pH probe is maybe 10 millimeters in diameter. We want to know what the pH is in these droplets that are present, or aerosols, which are 50 microns or smaller. You can't just stick the pH probe in there. So together with a colleague, Peter Vickersland, we've developed gold nanoparticles that we can seed into, functionalized gold nanoparticles that we can seed into some kind of suspension that we're going to aerosolize, and they have a pH sensitive dye, and then we can observe the Raman shift in those to figure out what the pH is in these droplets. And we find that if we start with phosphate buffer, which has a pH of 7.3 in bulk, just sitting in a vial or in a beaker, and we atomize that, when we look at droplets, we can get down to about 10 to 20 microns in size. We find that the pH is actually 10.5 in these. And so that's going to have big effects on the chemistry. And so we measured this for 33 droplets, and this just shows the distribution of pH, that in the bulk solution, it was somewhere in the range of 7 to 8, and in our droplets, it was in the range of 10 to 12. Probing a little bit further, we actually find a spatial gradient in pH in these droplets, and this is probably true for films too, where at the outer edges, the pH is lower, kind of that 7 to 9 region you can see here. But right at the center, the pH is 11. So we get this spatial gradient again, which is going to be interesting for the chemistry. And then it's really the combination of relative humidity and pH that affect virus viability. This is just one example from the applied to microbiology, but I think that this example here would have relevance for abiological just chemistry of VOCs or of organic compounds and other things that we're interested in indoor air. So this figure shows, again, MS2, our unenveloped virus, and Phi6, our enveloped virus. It shows the relative viability, where 1 or 10 to the 0 means that everything survives just fine. As a function of relative humidity, we looked at 3 different relative humidities, 20%, 50%, and 80%, and then at 3 different pHs, so pH of 4, 7, and 10. And for MS2, you can see that we see that kind of classic dip in viability at the mid-range humidity, but there's really not any kind of pH dependence. With the enveloped virus, however, we do see a strong pH dependence and some RH dependence, but where either at pH of 4 or pH of 10, we have greatly reduced viability. We've done this also looking at other solutes in the media protein. We find that we looked at sodium chloride, BSA, bovine serum albumin, as our protein and a surfactant. We found that protein is generally protective, which has been shown before, and we found mixed effects for the sodium chloride and surfactant. So when you are looking at these kind of droplets and films in the indoor environment, the chemical composition can matter, and the relative humidity also matters. And now, just to summarize, humidifiers are potentially an important source of non-volatile particulate matter in the indoor environment. Secondly, as I showed, bacteria survive best at high relative humidity, and viruses at low or very high relative humidity, and they don't survive well in the middle. And relative humidity dynamically controls the water content of particulate matter, affecting both its chemistry and its biology. Thank you.